So, have you ever stopped to think about what's really holding up this massive world of artificial intelligence? I mean, it's not magic, right? It's math. And today, we're going to pull back the curtain on one of its most critical but kind of hidden foundations: probability.
All right, let's picture modern AI and machine learning for a sec. Imagine it's this huge, impressive temple. It does all these incredible things, but it can't just float there in midair. It needs some serious, powerful pillars holding the whole thing up.
And here we go. This visual really nails that idea. You can see it right here, the temple of machine learning. Up top, you've got the cool stuff, like regression and classification, but zoom in on the base. What's actually keeping that roof from crashing down? What are those foundational pillars? Well, we're going to zero in on this one right here, probability and distributions. This thing is one of the most crucial supports in the whole structure, and that's exactly what we're going to dive into today.
Okay, so the word probability can sound a little scary, right? Maybe it brings back nightmares of complicated formulas from school. But what if I told you it's actually something you're already a pro at, something you use every single day, probably without even thinking about it?
I love this quote from the source material. It just puts it so perfectly. Probability isn't some weird alien thing. Nope. It's just common sense. It's our gut feeling, our intuition, but it's wearing some formal clothes, the language of math, just to make it super precise. Seriously, think about it for a second. When you look outside, see some dark clouds, and think, I should probably grab an umbrella, that's you calculating probability. Or when you pick a certain route to work because you just know the other one is going to be a parking lot, that's probabilistic thinking. See? You're already an expert.
So the first big step in machine learning is basically this: taking that gut feeling, that common sense we all have, and figuring out how to stick some numbers on it, how to give chance a formal language we can work with.
And the main tool we use for that? It's called a random variable. Now, I know, it sounds complicated, but stick with me. It's really just a fancy way of turning real-world stuff, like flipping a coin, into numbers. So instead of heads or tails, we just say 0 or 1. That's it. It's really that simple. And this is a great way to see the two main flavors these variables come in. Over on the left, you've got discrete variables. These are things you can count, right? Like if you flip a coin twice, you can get 0, 1, or 2 heads. Nice separate numbers. Then on the right, you have continuous variables. These are things you measure, and they can be pretty much any value within a range, like someone's exact height.
Okay, so we've managed to turn the world into numbers. Awesome. What's next? Well, now we hunt for patterns. We start looking for the shape that all these numbers create when you put them together. And that shape has a name. We call it a distribution.
Let's jump back to that height example. Imagine you're measuring people's height, but you're being kind of lazy about it. You just round to the nearest foot. So you get a bunch of people who are 5 feet, 6 feet, or 7 feet. Your data would look like a few chunky bars on a chart. A little clunky, right? It almost looks like that discrete data we just talked about. But what do you think happens when we start getting more and more precise with our measurements? I'm talking not just feet, but inches, then centimeters, then all the way down to millimeters.
Well, those clunky bars start getting thinner and closer together until they just blend. They melt into this beautiful, smooth curve, and that is the very essence of continuous data. It doesn't jump between points, it flows. That curve is telling us a story about the shape of our data. And this brings us to a really, really important kind of mind-bending point. With a smooth curve like this one, let me ask you, what's the probability that someone is exactly 170.0000 centimeters tall? The answer, and this might surprise you, is basically 0. Why? Because a single, infinitely thin line on this graph has no area. In the continuous world, probability lives in ranges. We don't ask about an exact point. We ask, what's the chance of being between 169 and 171 centimeters? It's all about the area under that curve. Okay, so now that we get the idea of these shapes, these distributions, let's talk about a superpower this knowledge gives us. It's the ability to compare things that, on the surface, seem completely different. Apples and oranges. Let me give you a classic example. Let's say you scored an 80 out of 100 on a test, and your friend scored a 70 out of 100 on a different test. Easy, right? You won. But hold on, what if your tests were totally different? Maybe yours was way easier. How can we possibly make a fair comparison then?
Okay, let's add some context here. Let's say the average score on your exam was a 60, but your friend's exam? Whoa, that one was much tougher. The class average was only 50. All of a sudden, just comparing your 80 to their 70 doesn't really tell the whole story, does it? It's not fair. We really are comparing apples and oranges.
So what's the fix? We need to find some common ground. And in the world of statistics, that common ground is called the standard normal distribution. Just think of it as a universal measuring stick. It's a perfectly balanced scale where the average is always 0, and we measure everything based on how far away it is from that center point.
Honestly, the absolute best way to think about this is like currency exchange. But instead of dollars and euros, we're dealing with data. We take your score, which is in exam A dollars, and your friend's score, which is in exam B euros, and we convert them both into one universal currency, and that currency is called the z-score.
It's like this quote says, it's like making all your data wear the same uniform. Once everyone's dressed the same, you can compare them fairly. It doesn't matter how different their original tests were. We've created a totally level playing field.
So after all that, what's the verdict? Who actually did better? Well, once we convert everything, your z-score comes out to +2. That means you're 2 standard deviations above the average for your test. Hey, that's really good. But your friend's z-score, it's a whopping +4. They were an incredible 4 standard deviations above the average on their super hard test. So when you compare them relative to their own exams, your friend was the clear winner, by a lot. And there you have it, just like that. By understanding the shape of the data, not just the raw numbers, we solved a problem that was impossible to figure out otherwise.
We've kind of come full circle now.
So let's go back to that temple we started with. That pillar labeled probability and distributions. It's not just some abstract idea anymore, is it? You now get the intuition behind it. It's about turning the world into numbers, finding the shape hidden in that data, and then using that shape to make really powerful, fair comparisons. You now genuinely grasp one of the absolute core foundations of all of modern AI. So I guess the only question left is this. Now that you understand this fundamental, powerful pillar of AI, what would you build with it?